Thank you everyone for joining us today. We'll be jumping right in here talking about how we can use VI-NVHSim as a software solution to accelerate road noise analysis. These first few slides will probably look familiar if you've attended an NVH simulator related webinar before from VI-grade, but of course let's start generic and we'll move towards the specific. This information is always worth repeating. So let's take a quick look at what NVH is. So it includes powertrain, sound and vibration. You can see some of those typical phenomena here: boom, shake, growl, tonal noises from gears and motors and so forth. Of course, not the focus of today. We'll be focusing more on road noise and vibration, from secondary ride and imbalances up to structure-borne and airborne road and tire noise. We also consider wind noise, usually a little bit separate from road, although the noise that we experience in the vehicle as we're going at various speeds that varies based on the road surface that we're on, the speed that we're traveling, and of course the characteristics of the vehicle. Typically we experience road and wind together. Not often are those truly separable, but from an engineering standpoint, there is great value in being able to separate those out. And oftentimes in the handling of these within the vehicle OEMs, they can be treated by separate groups. So it's important to be able to differentiate between road and wind, even though from the end user perspective, we end up experiencing those at the same time. And then, of course, we have everything else on the vehicle that makes sound or vibrates. There's a lot of things in this world that do one or both of those things: brakes, heating and ventilation, chimes, warning sounds. Now we're getting into the world of EVs and design sounds that then are added into the vehicle to improve that driver experience. All of this falls under NVH. Now, of course, sound covers a very large portion of these phenomena as we look at our frequency range, as we have highlighted at the bottom of the screen. Most of our experience can be conducted in that sound sort of field, but let's not ignore the fact that there's also a vibration component. Of course, we're talking about software solutions today. We're talking about a desktop simulator sort of solution, which is traditionally focused on sound only. However, let's not ignore vibration. Of course, we have simulator solutions in which the software we'll talk about today does have an avenue to vibration. And let's also draw attention to the fact that there's an overlap in the kind of appreciable frequency range that we have for both sound and vibration in that kind of 20 to 200 hertz range of things, and a little bit of plus or minus on either end of that. Oftentimes, especially from the end user's perspective, ends up being something where those are highly coupled. So that's a reason why both N and V are standing there in NVH. So why is it important? It's one of those main attributes that controls really the overall user impression of the vehicle. It comprises a number of various aspects. You can see here on the right between all of our various components that we'd started to highlight in that previous page. It's focused on the character, both interior and exterior of the vehicle. Oftentimes sound is the first level of experience that a potential buyer or somebody who sees a car for the first time, they probably see it first and then you hear it next, although I can imagine a few cases where you might hear it before you see it. All of that moving to support that it's a really important phenomena to be able to really have that level of control over it, so it delivers exactly what you want. It's usually highly tied into with that brand DNA, kind of the presentation in the marketplace of the vehicle. So NVH really brings it together. It affects that initial buying decision, being one of those first experience points that the end user comes in contact with. Also, longer term, as they experience the vehicle, are they going to buy the next one? Being able to maintain satisfaction over the lifespan of that vehicle, and also getting those customers coming back again, and really buying into the brand really has a major effect there. So many types of engineering data, and especially as we get into the world of simulation and CAE analysis, we can adequately express these visually. So if we see what we have here on the left, We've got some various analyses that are quite objective. So things like we have flow targets for exhaust systems or aerodynamics type analysis. We have crash, as we have here on this page. These are very objective. You can get everything you need pretty much from the visual representation of these data. When we get into the NVH space, of course, we have plenty of objective data to be able to pull from, and it's definitely very important. That's oftentimes how we judge targets, and it's the easiest and most direct touch point, especially when dealing with simulated data. Being able to understand how is this going to relate to the actual experience in vehicle. But it doesn't tell the whole story, especially when dealing with something that is so subjective. Everybody experiences noise and vibration. Those of us that have specialized in it certainly have an aptitude for being able to extract information from these plots. So they're quite useful, but they don't answer some of the really, really important questions that we have here in terms of the subjective experience. They don't tell us, does it sound good? Well, what does good mean? How much of a difference is impactful? It doesn't necessarily tell us that. It can tell us the two things are similar or different, but the degree of similarity or difference not always communicated through the visual means. From comparison sort of things, if you're looking at the NVH signature of your vehicle versus a competitor's vehicle, which one sounds better? That's something that it's quite easy to make that judgment as kind of the end user, somebody just approaching the showroom. You might be able to pull that out, but if you showed them the squiggly lines and graphs that we often immerse ourselves in as NVH engineers, it doesn't always come across in terms of that messaging. So to address this, we've created here at VI-grade our NVH driving simulators to enable that experiential simulation, being able to not only generate these plots taking in data from various sources, but actually give you the opportunity to experience those and answer some of these subjective questions. Does it sound good? Is it better than the competition? Well, what does it sound like? Which in the next video that we'll show here, I'll demonstrate the desktop NVH simulator, which encompasses only sound, but of course we can pull together that vibration in some of our other simulators that we'll talk about a little bit later on. So as a simulation tool, VI-NVHSim and the NVH driving simulators that we have here at VI-grade really function as data integrators. They bring together data from multiple sources into a single unified virtual prototype. Of course, this can come from test and measurement, CAE analysis, a whole variety of things all coming together from various sources. We have an open platform here at VI-grade where we can integrate from any and all input data sources. We do some degree of modeling. Certainly internally, there's a process for developing NVH simulator models, but oftentimes that actually relies on other forms of simulation and modeling that happen as input to this system. All of this comes together to enable us to evaluate the totality of all of these data sources, making sure that we can understand them, we can communicate them to a wide variety of stakeholders and make the correct decision based on bringing all these together in the most proper way. This allows us to really easily communicate both to specialists that we have that understand the squiggly lines and plots that we had a couple pages ago, but also to a wide variety of these stakeholders. So people in marketing, the chief engineers, program managers, people in the C-suite management, even going right to customer preference sort of studies. All of that's enabled. We all experience the sound just like we would the vehicle on the road. So this is my point now to introduce the VI-grade desktop NVH simulator powered by the VI-NVHSim software. I'll go right into a demonstration video here of the tool conducted by one of my colleagues.
Drive the future. Drive and experience the sound and vibration of vehicles interactively in a virtual environment. The best way to evaluate the NVH characteristics of a vehicle is to actually drive the vehicle. But what do you do when there is no physical vehicle to drive? How do you make NVH decisions with confidence? Whether existing vehicles or virtual prototypes, you can drive vehicles interactively and evaluate the sound of the vehicles just as you would drive a real car in a virtual environment. Evaluate vehicles back to back. Switch vehicles while driving. Easily compare the sound and vibration of vehicles for engine, electric motor, road, wind, or any other aspect or component. Capture customer preference. The vehicles driven in the simulator can be real existing vehicles, completely virtual vehicles based on CAE models and targets, or contain elements of both. The sound of the vehicle can be represented as several components, such as electric motors, engine, road, and wind sound, and can be further subdivided. These sounds can be derived from vehicle recordings or created from CAE models and data. The NVH simulator software is used to develop virtual vehicles and engineer new vehicle sounds. Apply filters and changes to the sound of the vehicle. Change the motor, gearbox, engine, exhaust, tires, and other components. The NVH simulator is the ideal environment for active sound design, designing and integrating electronic sound enhancement. There are several versions of the NVH simulator, all powered by the core NVH simulator software. The desktop NVH simulator is the primary workstation. The compact NVH simulator and static NVH simulator add vibration as well as sound. There is also the on-road NVH simulator and the exterior sound simulator. Listen to the sound of the vehicle before you build the car. Capture customer preference. Communicate design changes effectively and efficiently. Reduce the need for prototypes. Understand NVH data quickly and easily, and make decisions with more confidence than ever before possible. Drive, experience, understand, decide. The NVH simulator from VI-grade.
So we've introduced the desktop simulator based on the VI-NVHSim software. This is the core NVH software that's powering all of our NVH solutions here at VI-grade, all the way from the desktop solutions up to the full driver in motion and everything in between. Some highlights here. It enables us to build these virtual prototypes from either CAE data and or experimental data. So bringing together, like we indicated before, from various data sources, whatever level of information is available to be able to create these comprehensive virtual prototypes. As we saw in the video, it allows for instantly being able to switch between sounds, go back to back. We'll get into a little bit that later with our road noise demo here. Real-time interaction with sound. So it's all, we've got modes for both offline and online sort of things, whether we have driver in loop or more fixed playback sort of scenarios. We'll go through a couple of those again a bit later. And it's that open architecture. I'll draw some focus to that again, being able to bring together NVH data from any source, whether that be CAE or test and measurement or some combination of the both, bringing that together, including real-time integration with many of our third-party partners for what we call anything in the loop, software in the loop, hardware in the loop, sound design, some of the interactions that we've had with multi-attribute sort of simulation spanning across both vehicle dynamics and NVH. All of that comes together, really using VI-NVHSim as the hub for all of your NVH virtual prototyping needs. So with the introduction out of the way, let's introduce our challenge for today. So in the topic of performing road noise analysis, to set the scene, we have this engineering challenge here. We're designing a new vehicle based on a previous platform. As we move to the next generation, the goal is to improve the road noise that's experienced by the driver, as in this scenario, we've received complaints from drivers about the previous generation performance. But of course, those complaints are often not terribly specific in terms of the engineering work that requires doing. They can't tell us exactly which components need to be modified in order to improve the experience. We're not even sure how much reduction is necessary to be appreciable. Is it a problem across all speeds or just specific ones? Are there particular road surfaces that are making this problem worse? We actually have more questions than we have answers at this point. So let's hold on to this challenge a bit. I'm going to introduce some new functionality introduced to VI-NVHSim very recently that perhaps we could use to help address this challenge. So of course, with the recent, just about a month ago, we released the VI-NVHSim 2024.1 version. It contains a whole plethora of new and enhanced functionalities and workflows to support this virtual prototyping mission. There's a whole bunch on this page. We're not going to go through every single one of them. We're going to call focus here to one in specific. And that is our operating path analysis method for road noise decomposition, so-called OPA method. The function of this is to decompose our total masking sound that we may have from a measured scenario and decompose that into individual source contributions that we can study in great detail. We might want to do this to understand the root cause of specific road noise phenomena or to simply separate the road and wind noise. Remember in that early slide, what we had was the road noise, basically structure-borne and airborne radiating from the various tires. But also separately, we have the wind noise. We might want to be able to separate those. From a test and measurement standpoint, sometimes that's very challenging. Of course, you can go out and you can measure on a road surface. That's pretty straightforward. But whenever we make that measurement, always the road and wind noise come together as a package. It's not like I can call into the Weather Channel and have them turn off the wind for a day. Typically, you can get wind noise on its own through a wind tunnel type measurement, but not everybody has easy access to those types of facilities. They're often, of course, quite expensive to get test time on, and altogether somewhat challenging there. So to really enable some of this advanced analysis, it becomes quite advantageous to be able to take a signal that's comprised of both road and wind noise and separate them out to the various components. Historically, we've had options to be able to do this through post-processing methods. Classically, we've had, of course, the SPC, source path contribution, or TPA, transfer path analysis type methods. It's super powerful. Of course, you can get down to a great level of detail and really decompose any sort of kind of vehicle measurements there down into these sources and paths. That power comes with a cost. Usually requires very high channel count in terms of measurements and additional sensitivity measurements in addition to those operational tests. But of course, you get all the power of a transfer path type methodology there, being able to decompose down to individual sources. Previously, VI-NVHSim did include an option for road noise decomposition similar to the OPA that we called MCOP for multiple coherence output power. So it's a multiple coherence based method which performs some basic level of decomposition. It really just does it to the group level. If I specify here, it's really just this first level here. We can take this total and break it down into the three components, basically structure-borne road noise, airborne road noise, and the remainder, which we'll call wind noise in this case. So MCOP was great. It was quick, easy to process, required a minimal channel count relative to a full transfer path analysis. However, the best level of decomposition you could get was front to rear, airborne to structure-borne, separating your road and wind noise. Gets you part of the way there, but you lose a little bit more of that specific engineering level value. What we've introduced here for the 2024.1 release with this operating path analysis, it offers something that's kind of slots in between full transfer path analysis and the multiple coherence method of the past. What it allows us to do is to get not only down to the group level of structure-borne, airborne, and wind noise, but also down into individual source contributions from any of the reference signals that we measure. Still has a nice minimal channel count requirement. We'll get into that very shortly. It offers a greater level of detail than was possible with the multiple coherence method, approaching that of the source path contribution. Of course, we don't have the sensitivity, so it's a little bit difficult to say whether something is driven by high input source levels or if it's amplified by the sensitivity of the vehicle body structure, but it still gives us that level of going just a bit deeper. In addition, it offers a next generation of performance above and beyond what was possible previously with the road noise decomposition, in that it allows both steady state and transient operating conditions. So we can use this for classic road noise of measuring on a single surface at a single speed, kind of steady state conditions, but we can also use it for impact harshness, being able to understand the relative importance of the structure-borne and airborne components for transient type operating conditions as well. So a little bit more about the OPA, just to introduce that here. It's got a very minimal data requirement, much in line with typical NVH road noise evaluations for on-road type measurements. We've got a 22 channel count minimum, which is really not that high, especially as you compare it to something like a full transfer path analysis, which we can require 100 plus channels for something like that. Having gone through that experience multiple times, that is certainly not for the faint of heart. Super powerful, but like we said, it comes at a cost. So for OPA, we need, of course, our driver signals, being able to understand what the driver experience is, and then some reference signals located on the vehicle body structure. Typically, our minimum requirement that we recommend for this would be wheel hub accelerations on each of the corners, so front left, front right, rear left, and rear right, as well as tire patch microphones to get our airborne component of that. Typically recommend both leading and trailing sides of the tires, again, at each of the four corners. And then our operating conditions are quite simple. It's usually part of the standard test plan for any validation run for late stage prototype or for benchmark testing, being able to take steady state road noise at various speeds. We can process up multiple of those and generate an NVH simulator model from that. As well as being able to support the processing of impact events to understand the breakdown for impact cleats, speed humps, things of that nature. So this means that because we have a simple data set here, we could use an existing data set quite easily and then take advantage of the new post-processing ability of the operating path analysis. So if we remember our challenge that we introduced right before going on the little side branch there to talk about new features and highlight that operating path analysis, the great news is we can use this operating path analysis to decompose some road noise from the previous generation vehicle that we already have sitting in the database, to be able to understand a bit more about it and begin to plan for what does the next generation look like, independent from any of the powertrain development that's ongoing, independent from any new models that need to be generated. We can take advantage of data that's sitting on the shelf. So there's quite a happy story there. From this decomposition, we can study it to understand the key contributors to the road noise NVH metrics or targets, begin to understand what are the most key components, what's driving that overall level that our existing customers have been complaining about. And because I'm using VI-NVHSim to do this, I can perform this study both objectively through analysis and subjectively through listening and experience, allowing me to confidently make decisions about this. At the end of this, I'll know exactly how much to reduce, what to work on first, and I can plan efficiently and effectively my next steps in the development process. So without further ado, let's demonstrate how we can use the OPA data in VI-NVHSim. So here in VI-NVHSim, I have a model which includes the contents of my road noise decomposition. I've done this ahead of time using the operating path analysis functionality within the data prep tool. That's allowed me to decompose my road noise into individual contributions from each of my structure-borne and airborne sources, as well as separating out that wind noise. I've put a free driving model in here, which will just allow us to exercise this vehicle exactly as we would the vehicle on the road. So if we move to the car assembler, we can see I've configured a car assembly here with some subgroups. This groups some of my contributions together, and I can use this for some of the detailed analysis we'll perform here in a moment. So let's jump right in and we'll launch our simulation. All right, so the first thing we can do is actually start the vehicle. We'll activate the model so we get some sound. We'll remove the brake, put it in gear, apply some throttle. We'll see we'll begin to accelerate, and the road noise will follow. Might be a little bit low level on the call here, but hopefully you can hear that somewhat. Otherwise, you can see we've also got the objective data coming in. Now, one of the cool things we can do is actually create recordings just as we would with test and measurement data if we were to instrument this vehicle and run it on the road. So we'll configure that here inside VI-NVHSim. I'm going to use the BKC file format because I'm going to use BK Connect here in a moment for my post-processing. Of course, other file formats are available working with other software packages. I'll specify a recording name, just keeps it easy to keep track of a bit later. In that recording name, I'm going to put groups on the end of it because I'm going to use this channel selection for only playing groups. What that will do is provide some subtotals in my multi-channel recording file for each of the groups that I configured in the car assembler. I'm trying to understand what the key contributions to my road noise are, so using the subgroups is a first step, allowing me to localize to front, rear, airborne, or structure-borne. From there, we can do a deeper dive in subsequent analyses. So let's start. We'll make a measurement here driving from stationary up to about 130 kilometers per hour. We'll start the recording here, release the brake, and apply the throttle. The great news, since I'm recording just the simulation output, I can talk while the measurements are happening, and it doesn't contaminate my data. Anyone who's gone through that test and measurement process knows that's quite a nice thing. So we'll stop the recording. We'll bring the vehicle back down to stationary, although we could look away and nothing bad will happen. And we'll head over to BK Connect and let's analyze that recording. So I've configured BK Connect to automatically import the recording and process it according to a process chain I've configured ahead of time. That makes it quite easy to work here. So we've got here an overall dBA versus vehicle speed going from 5 kilometers per hour to 130. We can see that overall level increasing as we increase speed. This is for our total left channel. We can see here in the matrix, that's our driver left ear of our recording. Because I included the groups with the only playing groups option, I can overlay those here. So now we have multiple curves on that I can highlight those. I can look at the total and then going down through the various groups. So if we were to cursor on these to understand the relative levels of these, we'll see the front structure-borne up here at the top, moving below that, the rear structure-borne, and then down to the rear airborne, the wind noise, and then the front airborne groups. So just let's dwell on that wind noise just for a moment. We can see that really starts to become key as we exceed maybe about 120 kilometers per hour. That's really where it's starting to dominate. However, our overall dBA for road and wind noise is really dominated across the speed range by our front and rear structure-borne road noise components, not so much the airborne or wind noise components from this decomposition. So that's already, we're learning a bit. So let's head back to our NVH simulator model. We'll make some modifications so that we can understand the impact of changing only the structure-borne components. That'll allow us to understand if structure-borne really is our main contributor. So before we make our changes to our model and make another recording, let's think about this a little bit. In order to make the recording, we need to drive the vehicle again. And the whole point of simulation is we don't need to do things like that. One of the benefits of working in simulation is we can automate this process, improving the reliability, making sure we're always exercising exactly the same operating condition. It just makes us work a bit more fast and efficient and accurately. So through the recording that we made previously, we can actually configure a fixed driving test very easily. This allows us to really just exercise our model, but keep some of the operation of the vehicle in the responsibility of the simulator itself, offloading some of that to the software. So I'm just going to quickly here create a fixed driving test, taking the recording that we had from previous, and we'll use that sort of as a player piano type thing to be able to drive our analysis. As we load this up in fixed driving mode, we can see our RPM here. We can switch the column, look at speed. This is really quite easy and allows us to have exactly the same operating conditions as before, but now we can modify the sounds and get different outputs, really exercising our model. So I want to make some modifications to this model. I want to subjectively and objectively prove that these structure-borne components are the most important. Again, the squiggly lines told us that, but let's prove it out. We can really we can experience and get our hands dirty with these data here. So I'll open up the filter list, and I can quite easily apply a dB reduction to just the structure-borne groups that I have here. Note I could also apply frequency-dependent filters to be more specific, but for now I'm just trying to prove out the big picture. The overall dB is quite effective. I'll change the recording name to indicate that I've done that reduction. That way I keep things straight when I get into my post-processing, and we'll just make a recording. You'll note that all I've had to do was start the playback of our player piano roll, our fixed driving model, and it's driving exactly how we did during that first recording. That makes it quite easy as we go back and repeat the processing, wanting to really exercise and make this A to B comparison. For the subjective part of the evaluation, I don't remember what it was before, but we can really easily switch between the filtered and unfiltered states. That sounds pretty different to me with the structure-borne reduced. So subjectively, I'm pretty sure that that's a major contributor, but let's go check the objective data as well inside BK Connect. So by the time we switched over, we've automatically imported and processed our new run. So that's already shown here. It's pretty immediate, really switching between the two softwares. We have our reduction of 10 dB. I want to switch between the two runs that we've recorded, so I'll bring up the toolbar to be able to easily switch between the two recordings that I have. As I switch between these, I can see there's a pretty serious reduction in the overall level, but I might want to go channel by channel and investigate this a bit further, just make sure it's doing what I expect. So if I switch and then only view the totals, we'll pull some of those other curves off of here. We can see that I've got my 10 dB reduction just looking at the totals. We're going from the red, which is our original, to the blue, which is now our reduced. So that's quite easy. If we go down to the individual groups, we should see that the structure-borne groups are indeed reduced. But if we go to the airborne groups, we don't see any reduction. We really see that same performance across, which makes sense because we know we've only changed in the model the structure-borne components. So we've confirmed both objectively and subjectively that reducing the structure-borne components has a major effect. However, 10 dB, if we're looking at these, we've got our new contributions for the structure-borne. They're now way below what the other contribution groups were. This is a bit exaggerated for us to actually design towards. I think if somebody came in and said we need a 10 dB reduction, we'd start to get really wide-eyed in terms of what of a daunting task that might be. So instead of the 10 dB reduction, which we've done just to prove out that, yes, that's a very important source of this, let's see if we can come up with something a bit more subtle that still has an impact, but is a little bit more reasonable from a target perspective. So we'll do a little bit of cleanup here, just reselect our time range, getting out of our subjective mode and back into the objective mode. And then let's, instead of a 10 dB reduction, let's try something that's maybe only about 4 dB. It's a bit more reasonable, and then we can go and modify our filters accordingly to make sure that we've just got the structure-borne down by 4 dB. Again, we're just using that fixed playback again, so it's going to be exactly the same time history that we had, the same driver demands, those same parameters. The only thing we've changed is then the overall levels of our structure-borne groups. As before, we can configure this loop and do a bit of subjective analysis. That's a bit more subtle now, especially not having the calibrated headphones of the desktop simulator, but we can see what the data says. If we look at this, our contributions are all in the same ballpark now, so that's good. If we compare this to the original recording again, we can see the original recording's now blue, and we're now at the red with our 4 dB reduction. We can see that's still appreciable, at least in terms of the objective standpoint across all speeds. So the question remains, and we can look at the structure-borne group for this. What do we need to do to achieve this 4 dB reduction in the structure-borne group? I'm plotting just the fronts here, but the same applies to the rear. Which sources, which area of the vehicle, what do we really need to focus on in our design work that we can effectively make a change that then cascades to this level of target performance? So to answer this question, we're going to use another functionality of VI-NVHSim, and that's to actually provide output for all of the single objects in my test. So I'll change the file name here to include the word objects. The reason for that, we'll do a little other cleanup of my file name as well. But the reason for that is we'll use the only playing sound objects channel selection option. So now instead of the groups, we'll get actually an output for each of the objects that I have. So these are each of my individual road noise contributions that I have developed using my operating path analysis. So again, we'll restore the original performance because we really want to look at what the main contributors are to those structure-borne groups in the overall. And then I'm also going to use the solo and hold functionalities here to parse down my channel count so that I'm only including channels for the structure-borne. Let's filter out the rest. We need to focus on the structure-borne. Let's be efficient in our analysis. And so we can indicate that in the recording name and then make a new recording. Of course, subjectively, this sounds a bit strange because now we're listening to only the structure-borne components of that road noise, but really the purpose here is to enable some of the deeper analysis here at BK Connect. So we can see the front structure-borne, and if we reconfigure this here, if we bring in both the groups and the individual objects recordings together, I can actually overlay the group subtotal with the individual members of that group. So for the front structure-borne, we've got the overall level across our speed range at the top, and then all of the contributions exist underneath it. So those summed up equal that red curve. If we break this down by speed range in the lower, kind of below 40 kph, we've got this one standout, our front left corner in the lateral direction. That's the Y direction globally on the vehicle. It seems to be dominating there. That could be something we go back and look at the vehicle design, see if there's something we can do to improve the contribution from that. Maybe there's a sensitivity resonance in that direction to be able to reduce the overall level in that range. So we go to the mid-speed range. We've got a couple lower contributions, but most of them are pretty consistent across the range. The lower ones are front left X and front right X. So that's our longitudinal directions. Those don't seem to be quite as important in this speed range. So really, if we're looking to drop the overall level in the mid-speed range, we'll have to focus on the great majority of these sources. So we've learned that maybe a bit more study is required there. As we go to the upper speed range, we've got a couple that are dominating. These are our front left and front right in the vertical direction. So that's maybe an area that we could focus on. If that's an area of the speed range that we want to try to reduce, we can focus on only the vertical inputs through the suspension. That simplifies, of course, our next steps quite a bit. So now let's not forget about the rears. We'll move to that. We'll get those overlaid here and do the same sort of breakdown. So again, we've got our overall level up top in red and all of the contributions that sum to that underneath it that we pulled from our OPA. In the lower speed range, now we've got two standouts here. These are both of the corners in the lateral direction. So we've got that in common with the front, where the lateral direction seems to be the area to focus on if we want to improve the lower speed range. So we get into the mid-speed range, 40 to 90, 40 to 100 kph again. Most of the contributions are pretty consistent, a couple low ones again, but that's actually the right vertical direction and left vertical direction, which are less important in the rear of the vehicle than they seem to be in the front, doing that level of comparative analysis. And then as we get into the upper speeds, it seems to be a bit more dominated by perhaps the right lateral direction. Seems to be consistent across, honestly, most of the speed range here in the rear. So that's probably our first place to look at is lateral inputs in the rear of the vehicle, seeing if we can reduce the sensitivity to that to be able to improve our rear structure-borne component of the road noise. So overall, just to summarize what we've done here, we've used the operating path analysis method to decompose our road and wind noise from some data we had sitting on the shelf down to individual contributions from each of the corners, both structure-borne and airborne. We've used these data to construct an NVH simulator model, which we've exercised using VI-NVHSim, as well as post-processed recordings that we've generated in VI-NVHSim using BK Connect. This has allowed us to both objectively and subjectively analyze our OPA results so that we can understand the key contributions to our road noise and focus our analysis as we move deeper into our development process. This allows us to be both efficient and confident in our next steps as we're pursuing our better NVH performance for road noise. So just a bit more summary, kind of pulling some of those highlights out in specific in text here. We highlighted a detailed road noise model, breaking down, decomposing some measured data that we just had available in the database from our previous generation vehicle, using the new operating path analysis method for road noise decomposition, breaking that down, separating our road from wind noise, as well as breaking down to the individual kind of XYZ components that we have at each of the four corners, as well as the airborne components. We learned from that we're able to focus in and understand specifically what has the most impact to that overall road noise. Of course, we could have just looked at plots, those squiggly lines from the OPA output, but really bringing the data to life using VI-NVHSim allowed us to do a much more complete analysis. It allowed us to take specific operating conditions from the vehicle that were not predetermined. All of that model was generated based on steady state measurements of our vehicle, but we were able to do a speed sweep and evaluate very quickly across that, as opposed to having to analyze at specific speeds, so 30, 50, 60, 80 kph, and run that analysis multiple times. Instead, we could do a speed varying analysis and really get that breakdown across the whole speed range in a simplified method. It was quite nice. We can also connect that, of course, with the subjective impressions of things. So when we made the 4 dB reduction, making sure that we could appreciate what that was as a target setting exercise, it's really important to make sure that we're setting targets that actually matter. If somebody's pushing for something that's an additional 3 dB, but we know that that 3 dB is not going to be heard by the driver, let's spend our time working on something else. Let's make sure that we're being efficient and effective in our design work. And that was all enabled by, again, bringing our NVH data to life, not just looking at the plots and the data that we could generate from these analyses. We could then even go a bit further because we're using VI-NVHSim, and that's generating time history data. We can merge that right into our normal NVH analysis workflow. We used BK Connect in this demonstration, although with the other file types available coming out of VI-NVHSim, and again, leveraging our open architecture that we have, that could easily connect with any of the other available NVH analysis methods that you might have, that you're comfortable with working with, that you use for other normal vehicle development processes. That's now enabled through the recording functionality that we demonstrated today through VI-NVHSim. And all of this really culminated in leveraging our road noise decomposition to efficiently guide our future development efforts. Perhaps if we need to go to a level of a TPA or SPC type analysis, we know now that the structure-borne is most important. And if we're focusing on the front or the rear, we know specifically some directions and maybe areas of the vehicle left to right that are most important for us that we can use. To be a little bit more specific with that, we don't have to worry about the airborne component, so that cuts down the complexity of doing further analysis. We know we can focus our efforts to where it's most effective, and that's was really advantageous here because we could take advantage of pre-existing data on the shelf because the data requirements of the operating path analysis are very minimal and flexible. We used that 22 channel count set. You can use more if more is available. If you don't have quite so much, it's still possible to use. We still give that ability to separate it out into those individual reference signals. So just to kind of reiterate some of the summary points of using VI-NVHSim as a software solution powering an NVH driving simulator, it allows us to evaluate our NVH data efficiently. We can experience the sound and vibration data as well as generate our objective metrics. Bringing both of those together really helps us do things in an efficient and quick manner. And we're doing it right. Everything's calibrated within the simulator architecture. The levels that we're getting out are actually the levels that we anticipate based on the data sets that we've populated the model with. So we can decide on these sorts of things with confidence, making sure that we've got things accurate throughout the process. Everything's validated, everything's equalized and presented in the same manner as it would be if you were to build something or you had the ability to physically separate road from wind, front from rear, airborne from structure-borne. We have confidence in the analysis methods and returning exactly the values we expect. All of this works together to save time. I think we could all afford to spend a little bit less time doing the things that take a lot of time for us, and this is really a great way to leverage the time that we have. It's always a finite resource, so how can we do more with the same time that we have? Some of this has really enabled us to do quite a lot in that 15-20 minutes that we spent in the software there. Would have taken quite a bit longer had we had to do a bit more storytelling or experimental type analyses to be able to tell that story. And of course, if we're saving time, we're also reducing cost. If we don't need access to a prototype vehicle or renting another existing vehicle to get a new data set, or quite frankly, the prototypes just don't exist. So being able to pull in data from various sources, whether that be test and measurement or CAE or a combination of both, it allows us to use virtual prototypes in place of physical prototypes in the NVH engineering process. So less time spent on that and better decisions. We make less mistakes as we go through. We make effective choices, making sure that when we're making a change to the design, we know that it's going to make an impact. That helps us be, of course, very efficient and have cost savings in that standpoint. So overall, quite a few benefits of working in the virtual space, and even as our hands are being forced by the reduction of prototype fleets, it's actually enabling us not only to survive and continue to work in the way that we have, but actually accelerate things and do things that were not possible before. So of course, we talked about the VI-NVHSim software. This powers all of our NVH driving simulator and solutions here at VI-grade, going all the way from desktop-based systems that do audio-only sort of things, all the way up through our compact, static, and dynamic simulators, which start to impart more and more of that driver immersion into the system. And of course, now the VI-NVHSim software, of course, works with all of our family members across the VI-grade solutions, including VI Car Real Time for vehicle dynamics, VI Graph Sim, VI Drive Sim, and VI World Sim. All of these working together to provide, again, that virtual prototyping ecosystem that allows for complete evaluation and experience, both objectively and subjectively, of not only NVH, but across multi-attribute as we start to get into areas where multiple teams and aspects of the vehicle have interaction to one another. So all of these, any one of them on their own or multiple sets of them working together, all come together to produce that comprehensive vehicle prototype. So again, just to hammer this home, VI-grade and VI-NVHSim and our simulation solutions offer the only complete, open, accurate, and proven solution for NVH simulators and simulation on the market. Again, bringing together all of the possible data sources that we have for NVH data, bringing those to life so that we can make better NVH decisions faster and with more confidence. Which brings me to our final slide for today. It's our promotion for everyone that has joined us today. Thank you very much for joining us. We'd like to offer you an opportunity to join one of our forthcoming online VI-NVHSim software trainings with a sizable discount. We're going to be offering those worldwide. It'll be a 2-day event. We'll do half days to make sure that we can we get a section of time window that's appropriate for everyone across the world on May 7th and 8th, coming up here in a little bit less than a month. The idea with that is you can scan this QR code and sign up for that training, and then you'd receive a free of charge demo license for 30 days to be able to take advantage of the power that you've seen here in the demonstrations, as well as many, many more. We'll be going through more of a generic basic level of training, getting you to the point where you could exercise the software just like we did here on this call, whether that's for road noise or powertrain noise, EV, combustion engine, whatever you have, sound design. We could cover anything you like in that space. So you do need to scan this QR code and sign up for that so that we can make sure that we're prepared for you in that space, and so you can take advantage of the discount that we have here. And then, of course, keep in touch with us as time goes on. We're always offering more of these things as we progress. So that's all I have for today. So thanks very much for your attendance, and don't hesitate to reach out if you do have additional questions. You can find me on LinkedIn. I'm sure there's some contact information floating around with the marketing material for this webinar. I'm always happy to entertain those.